Welcome to Lecture 10 of How to Read and Do Proofs. Welcome back, everybody. Today we're going to continue our study of the contradiction method, but actually learn a new proof technique called the contrapositive method. So first, let's take a moment to review the contradiction method. You'll recall that the idea of the contradiction method is to rule out the one case when A implies B is false. And how do you do that? You assume that A is true and B is false, that is, not B, and you work forward to reach some kind of a contradiction to something that you absolutely know is true. And when should you use the contradiction method? When you see the keywords no or not in the conclusion or anywhere in the backward process. Let's again take a moment to compare contradiction with forward-backward. As you recall, with the forward-backward method, you can assume A is true. Your job is to show that B is true. And how do you do that? You work forward from A and backward from B. With the contradiction method, what should you assume is true?
A is true and not B is true?
A and not B. And what should you try to conclude?
A contradiction.
A contradiction. And how do you do that? You work forward from A and not B. So from this diagram, you can see that the advantage of the contradiction method is that you get to work forward from two statements, whereas with forward-backward, you only get to work forward from one statement. On the other hand, you'll recall there's a disadvantage to contradiction. What is the disadvantage of contradiction?
You can't work backward.
How can you work backward from a contradiction that you don't know? So you cannot work backward. The advantage of the proof technique you're about to learn now is that it is a proof by contradiction, but you will know the specific contradiction that you're trying to reach. And if that's true, if you know what the contradiction is going to be, what can you do?
Work backwards?
You can work backward, exactly. And that's a tremendous advantage with this technique. So this is the idea of the contrapositive method. The contrapositive method is a proof by contradiction in which you assume A is true and B is not true, but now you try to reach a very specific contradiction. What contradiction? The contradiction that A is not true. Can somebody tell me, why is not A a contradiction?
Because we assumed that A was true?
Right. How can A be true and not true at the same time? That's the contradiction. Let's put it in a little table and look at it. With the contrapositive method, you can assume A is true and B is not true. Your job is to show that A is not true, because that will be a contradiction to A. And how do you actually do this? You work forward from A and not B, and backward from not A. Let's compare this with contradiction. With contradiction, what do you assume?
A and not B.
A and not B. And what do you try to conclude?
A contradiction.
A contradiction. And how do you do that? You work forward from A and not B. So can somebody compare contrapositive to contradiction? What do you see that's similar?
What you assume and what you work forward from.
What you work forward from, namely A and not B. That's the same. What else do you notice when you compare contrapositive and contradiction? What's the advantage of the contrapositive method?
You can work backward.
You can work backward because you know where you're trying to go. And that is the advantage of the contrapositive method. All right, now, again, because the contrapositive method is a proof by contradiction, you should use the contrapositive method under exactly the same circumstances that you would think about using the contradiction method, namely when? Go ahead.
When in the conclusion you see the words no or not.
When you see the keywords no or not in the conclusion or anywhere in the backward process. Exactly. So let me ask another question. Look at this diagram up here. Let's say we're going to use the contrapositive method. We need to get to the statement not A. We need to show that A is not true. How useful do you think it will be to use the assumption that A is true to show that A is not true?
Probably not that helpful.
Not going to help you at all. So in particular, with the contrapositive method, although we assume that A is true, you're not going to use A in the forward process. It's just going to sit there and help you reach a contradiction. And thus, with the contrapositive method, you can assume A is true and B is not true. Your job is to show that A is not true. And you'll do this by working backward from not A and forward from not B. A will just sit there passively to help you reach a contradiction. In fact, you can think of the contrapositive method as a passive form of contradiction in which the statement A just sits here and helps you reach a contradiction. In summary, you can think of the contrapositive method as the forward-backward method applied to the statement not B implies not A. You work forward from not B and backward from not A. It's kind of interesting to look at the truth table for not B implies not A. And what you will see here is that A implies B and not B implies not A are logically equivalent to each other. That is, they are both true under the exact same conditions. Let's take a look at the truth table for A implies B, and let's create the truth table for not B implies not A. So let me show you how we create this truth table. Look at the column B, true, false, true, false. Not B is the opposite, false, true, false, true. Look at the column A, true, true, false, false. Not A is the opposite, false, false, true, true. Now let's understand, when is the statement not B implies not A true? Well, we agreed that an implication is true in all cases except when the statement to the left is true and the statement to the right is false. The statement to the left is true and the statement to the right is false. Not B implies not A is true in all of these cases except when not B is true and not A is false. So, not B implies not A is true in all of these cases except this one. Look now at A implies B and not B implies not A. How are these two columns related to each other?
They're the same.
These are the same. And that means that A implies B is true under exactly the same conditions that not B implies not A are true. So if you want to prove that A implies B is true, you can do that, for example, with the forward-backward method. Or you can prove that not B implies not A is true, for example, with the forward-backward method. Again, to get a better understanding of this contrapositive method, let's look at comparing the contrapositive method with the forward-backward method. Here it is. With the forward-backward method, you assume A is true. Your job is to show that B is true. You work forward from A and backward from B. With the contrapositive method, you assume A is true and B is not true, but you only work forward from not B. Your goal is to show that not A is true, and you can work backward from there. What similarities do you see when you compare the forward, backward, and the contrapositive methods?
You can work both forward and backward.
In both cases, you can work forward and backward. In fact, from how many statements?
One statement.
And down here?
One statement.
One statement. So you're working forward from one statement, and you're working backward from one statement. What's different between these two methods then?
You use the negation of the statement?
Yes, the statements that you're working forward and backward from are very different. Up here, you're working forward from A and backward from B. Down here, with the contrapositive method, you're working forward from not B and backward from not A. These are very different statements. Let's take a look at an example. The definition I'm about to show you is meant to capture the concept of a property of a function in which whenever you put in two different values into the function, you get out two different values. So here is a formal definition. A function f of one real variable is called one-to-one if and only if for all real numbers x and y that are different from each other, when you put them into the function, the values that you get out from the function are different. So let's take a look at an example. The function f of x equals 1 plus x is one-to-one, but the function f of x equals x squared is not. Let's see, why is f of x equal to x squared not one-to-one? What two different values can you put into the function and still get out the same number?
A negative, like -5 and +5?
-5 and +5. If you put -5 in here, you get 25. If you put +5 in here, you still get 25. You can put in two different values and get out the same value. This function is not one-to-one. Okay, let's prove this proposition. If m and b are real numbers with m not equal to 0, then the function f of x equals mx plus b is one-to-one. So of course you have identified your hypothesis A, your conclusion B, and hopefully chosen a proof technique to get started with. Do I have a recommendation for which proof technique to get started with?
There is the keyword not, so it would probably be the contradiction method.
Yes, there is the keyword not here, m not equal to 0. But where is that keyword located? In the
statement A.
In the statement A, in the hypothesis. That is not the trigger to use the contradiction method. When should you use the contradiction method?
When the keyword not is in the conclusion.
When the keyword not is in the conclusion. So let me ask again. What proof technique would you therefore think about using to get started?
The forward-backward method?
The forward-backward method. So let's use the forward-backward method and, of course, ask the key question, how can I show that?
That a function is one-to-one.
How can I show that a function is one-to-one? And, of course, we use the definition, as we have learned to do many times. I must show that for all real numbers x and y with x not equal to y, mx plus b is not equal to my plus b. Look at b1. What proof technique would you use next, and why?
The choose method?
The choose method. Now the question is, how does the choose method work? In particular, what should you choose?
Two real numbers, x and y.
With?
X does not equal y.
Choose real numbers, x and y, with x not equal to y, for which you must show that what?
Mx plus b does not equal my plus b.
Mx plus b is not equal to my plus b. Now we have to fill in the details here of our model proof. This is the choose method. We have to fill in the details of the model proof. To do that, I have to work forward from A1 and backward from B2. Do you see any key words?
Not.
Not. Where do you see the keywords not?
In the backward method?
You see it in the backward process. Do you see it somewhere else?
In the forward process.
In the forward process. You see it in both cases. But what triggers the use of contradiction or contrapositive is this keyword right here. The keyword no or not in this case, not equal to, in the backward process. So in this case, I propose to prove that A1 implies B2 by contrapositive. So can somebody remind me, how does the contrapositive method work to show that this implies this? You should assume what?
That mx plus b is equal to my plus b.
And what do you have to show is true according to the contrapositive method? Not A1 in this case. So what do you have to show is true? What is the not of A1?
That x equals y.
You must show that x equals y. And this is very easy to do. Let's work forward from A2 to get to B3. How do we work forward from A2? Subtract b from both sides, and then what?
Divide by m.
Divide by m. Can you always divide by a number anytime you feel like it? When can you not divide by a number?
Oh, if that number equals 0.
If that number equals 0. But from the hypothesis, we know that m is not 0. If you look back at the hypothesis of this proposition, it says m is not equal to 0, and that's where we use that to divide by both sides. And that completes our proof. Let's see an example of reading proofs. So let's go back to a definition we've seen before. An integer a divides an integer b if and only if there is an integer k for which b can be written as k times a. So again, 5 divides 20 because 20 can be written as 4 times 5. Here's what we want to prove. Assume that a and b are integers with a not equal to 0. If a does not divide b, then ax squared plus bx plus b minus a has no positive integer root. Now I'm going to put up a condensed proof and ask you to take a few minutes to read it. Okay, our goal is to understand each of these sentences in the context of proof techniques. So, of course, you've identified the hypothesis A and the conclusion B. And now what we want to do is interpret S1. So let's read S1. Suppose that x strictly positive is an integer for which ax squared plus bx plus b minus a equals 0. Where did the statement S1 come from?
It's not B.
This is exactly the statement not B. What is the statement not B? Let's look at the statement B. Ax squared plus bx plus b minus a has no positive integer root. So what is the negation of this statement? Ax squared plus bx plus b minus a, what?
It has positive integer?
Has a positive integer root, and that's exactly what the author is writing here. Suppose that x greater than 0, positive, is an integer root. This is precisely not B. And that means what proof technique is the author using?
The contrapositive.
Could be contrapositive or contradiction. How will you decide which one? What is the author claiming in S4?
That A does divide by B, so
That
he's
A does divide B, and so that is what?
not A.
That is not A, and that's precisely the indication that this is a proof by contrapositive. Now we know that this is going to be a contrapositive method. So what should the author assume? That B is not true, which is precisely what the author has written here. X greater than 0 is an integer for which ax squared plus bx plus b minus a equals 0. And what does the author have to show? That A is not true. In other words, the author must show that A does divide B. All right, so now what? We should be working forward from here and backward from here. All right, let's see what the author writes next. The author then writes, then x is equal to minus b plus and minus b minus 2a all over 2a. Can anybody tell me where does that statement come from?
Working forward from not B.
Yes, working forward from not b. The author is solving this quadratic equation for x. So you know how to do that, right? X equals minus b plus and minus the square root of b squared minus 4ac all over 2a. And now let's just do a little bit of algebra here. Minus 4ab plus 4a squared. And let's do a little more algebra. This is b minus 2a, the quantity squared. And when you take the square root of that, you're left with minus b plus and minus b minus 2a all over 2a. And that's exactly what the author has written here. So again, you have to fill in details that the author has omitted. So that's a forward step. X is equal to minus b plus and minus b minus 2a all over 2a. Here's where we are. Let's see what the author writes next. Because x is positive, it must be that x equals 1 minus b over a. So first of all, how do we know x is positive? Ax squared plus b minus a has a positive integer root, right? So x has to be positive. Where does this come from? X equals 1 minus b over a. Well, let's look at these two roots. Here is the first root, the positive root, and over here is the negative root. Let's look at the positive root first. Minus b plus b, the b's cancel. You're left with minus 2a all over 2a, otherwise known as minus 1. We know that x has to be positive, so how can x equal minus 1? Can it? No, of course not. This cannot happen because x is a positive integer root. So if this root cannot happen, what must happen? The negative root. Okay, and let's clean this up. Minus b is minus 2b. Minus a minus 2a is plus 2a. So we get minus 2b plus 2a all over 2a. And if we simply cancel the 2's and do a little bit of algebra, we in fact get that x is equal to 1 minus b over a, which is exactly what the author has written here. Then the author writes, but then b is equal to 1 minus x times a, and so a divides b. If you want to understand this statement, you have to work backward. And now you should ask the key question, how can I show that?
An integer divides another integer.
An integer divides another integer, for which we have a definition. According to the definition, the author has to show that there is an integer c such that b is equal to c times a. What proof technique would you use to show that b1 is true?
The construction method.
The construction method, because you have to show that there is an object with a certain property such that something happens. So we need to use the construction method, and that's exactly what the author is doing. The question is, what is the value of C, because that's what has to be constructed. So here's where we are. To get that integer C, let's turn to the forward process and work forward from here. So in particular, let's do some algebra here. We want to show that B is equal to some number times A. Let's solve this for B. So multiply through by A, you get AX equals to A minus B. Just multiply both sides by A. Bring the B over to this side and the AX over to the other side. And now factor out A. Can somebody tell me what value do we construct C as so that B is equal to C times A?
1 minus x.
1 minus x. That's exactly what the author has done here. Constructed C is equal to 1 minus x. Notice that the author doesn't mention the construction method, but simply says, then B is equal to 1 minus x times A, and leaves it to you to understand that this is the construction method. The proof is now complete because the author has shown that, in fact, A divides B, and that's what we had to show to complete the contrapositive method. Let's summarize the contrapositive method. The contrapositive method is a passive form of contradiction in which you assume A is true and B is not true, and work forward only from not B to reach the contradiction that A is not true, and therefore you can work backward. The advantage of the contrapositive method is that you can work backward because you know where you're trying to get to. The advantage of the contradiction method is that you have two statements to work forward from instead of just one. Again, the time to use the contrapositive method and the contradiction method is when you see the keywords no or not in the conclusion or in the backward process. That completes this lecture.